ideas, and at least I stated the implications of one to the other. Some of them I may prove subsequently, but at present now I want to look at other questions about convergence. One major question about convergence is that of related to integrals. What I mean by that? So suppose I have some measure space. Do it in general case itself. You can take the real line if you want, but the general measure space. And that is omega is any set, P is the sigmoidal of set, mu is the measure of that set. The typical model is the probability case, if you want. Then you have a sequence of measurable functions. Probability is a sequence of random variables. Okay. Then, since Fn are all measurable, for measurable functions, integral Fn d mu are all defined. Because for any measurable function, we have defined how to explain how to define the integral. Now, therefore, we may ask the question: does integral Fn d mu omega converge? Now the integral Fn d mu is a sequence of numbers now. Once you have integrated out that function, you get a sequence of numbers. Does the sequence of numbers converge? And more so, we would like to push that limit inside, whether it is equal to that, but we don't know whether the limit exists. But we don't even know if limit exists. So we don't know whether the sequence converges at all. So now what we do is, well, first of all let us start with, I don't know any information about the convergence of the sequence. But one advantage with measurable functions is, you can do a lot of things and still get a measurable function. We know that whenever you have a sequence, whether the limit exists or not, the lim min and the lim sup will always exist. And because these are measurable functions, the lim min will also be measurable and so on and so forth. Okay. So first of all, observe, since Fnx are all measurable functions, lim min of Fnx, which I will call it as Fx, is also a measurable. Okay. So therefore, well, even if I cannot put the limit inside, can I at least put the lim min inside? So it is meaningful to ask, is lim in of the integral. This always exists. This is a sequence of numbers. The lim in of a sequence of numbers always exists. Is this equal to but this is the same as we have called this as lim min plus f. Okay, so is this. So can I push the lim min inside the limiting process? Can I interchange lim min and integration? That is the question. So this question makes sense. Okay. So this is the first question regarding the interchange of integration and a limiting process. So let's look at some examples. Let's take omega to be 0, 1. The rest of it is clear. The Lebesgue measurable subsets of 0, 1 and the Lebesgue measure. Okay. B, Lebesgue measurable subsets of R, mu, Lebesgue measure of then consider this 0, 1. Take 1 over n. Take 1 and 0, 1 over n 1 and 0 elsewhere. So let's take okay. So that's how we define the sequence fnx. They are all measurable because it's a characteristic function of an interval. So fnx measurable. Right. Then, what about for any x? Take any point x in this interval 0, 1. After some stage 1 over n will cross to the left of x and therefore fn will be equal to 1. So for any x in 0, 1, fnx equal to 1 for all n beyond a certain stage. That means the limit fnx is equal to 1. After some stage everything becomes. Therefore fnx converges to fx is 0. And therefore lim min, what is fx? Therefore lim min fnx, whenever the limit exists, what is the lim min? It is the limit itself, so is equal to 1 for every x. So what is the integral of lim min fnx? We have to integrate this function over the interval 0, 1, which is exactly. On the other hand, what is fn dx? I am integrating this function, which is simply 1 minus 1 by s. And this converges to or limit integral omega fn dx is exactly equal to 1. But whenever the limit exists is the same as lim min. So we have taken a case where the limit itself exists. So what happened? I got lim min is equal to, so therefore lim min integral fn dx is equal to integral fn. So it was okay. This question does make sense. At least in some examples, it does make sense. Now let me look at another example. Let's take omega to the 0, 1 again. B mu as before. Now let me look at f prime x defined as follows. I take the 0, 1 and take somewhere half, 1/3, some point there. Okay, this is actually there. Now what I do is, I make all the even functions to be 1 here and 0 here. And all the odd functions to be 1 here and 0 here. So, f2nx is equal to the characteristic function of 0 half, and f2n minus 1x is equal to the characteristic function of half. Now, what is, first of all, what is this? I want to calculate the limit. No matter how far in the sequence you go, it always takes the value 0 at that point, because x will lie here or here. If it lies here, however far in the sequence you go, there are even fellows who make it 0 here and vice versa. So the fkx is always 0 beyond any stage. So the infimum is equal to 0. Well, therefore, what is the limit? Is 0. So what is the integral of limit? 0. On the other hand, what is integral f and d? Integral.
It exists half.
It is always half. Whether it takes even fellows or odd fellows, it is always half. Therefore, the limit, which is the limit also. So these two are not equal. The limit we have got, in this case, strictly greater than integral. So we have got an example where they are equal. We have got an example where one is strictly greater than the other. Now what the first result on this direction was the lemma, which is known as a lemma. It's known as a lemma because all other theorems follow from that. It's like I will keep it as a base and get to the other theorems. That for non-negative function, these are the only two cases. If you take non-negative measurable functions, the limit of the integral will be either equal to the integral of the limit or greater than the integral of the limit. And that is what is known as the first limit. Okay? So, for non-negative measurable functions, these are the only two possibilities. This is known as Vittal's lemma. I will write the lemma over here. I cannot understand, I still don't know exactly why something is called a lemma and something is called a theorem. And generally, the lemma is supposed to be something pulled out in order to stop, in order not to interfere with the continuity of thought and put that thing somewhere. If this were true, then I will proceed and I will come back to that and prove it. And eventually, in many cases, there have been a few lemmas which have been more useful than the main theorem itself. And Vittal's lemma is one of them. Once again, I remember one test where I had with the same gentleman, Professor Zing, where he gave a question about convergence and this integration, exchange of the limit and the integrals. I really had no clue of what was going on. So what I did was I split everything to non-negative because any integral is in terms of f plus and f minus. So let me handle everything because if I split, I have Fatou's lemma at my disposal. And then I went on applying Fatou's lemma and got the result. It took me quite a bit of time. But then he gave me full marks. There was a shorter way of doing it. He wrote a comment saying, I don't know whether you understood the problem or not. You have certainly understood Fatou's lemma. So, the problem could have been solved much easier. But in the exam hall you don't get the. That's why I like the exams, the qualifying exams in the university I wrote at that time. They used to give 3 problems for 4.5 hours. You can go and get a cup of coke or a coffee and then walk in the corridor for a while, get back and then try to solve the problem. And it gave enough time to think. This business of you write 60 questions in 48 minutes or something like that, that is not that. You are given time, you think, and you try to get the answer. So there was enough time for you to think. It is not that. In fact, I think that is the only way to conduct maths exams. It is not this first-ish. Though I do give multiple choice and all. That is because we are in the system. Okay, what does Fatou's lemma say? Omega b mu is a measure space. Fn until omega to r, non-negative measurable functions implies limit integral omega Fn d mu always greater than or equal to integral. My friend, this is the main theorem about limiting process. Okay. So now what I will do, I will not prove this theorem at the moment. I will come to the proof of this theorem a little later.
So,
yeah.
So the equality, when does that equality hold? Is it
very hard this way. You will see. You can consider all kinds of crazy examples. There is no specific statement that says equality will take place equal only if. That is very difficult. Because you see, there is hardly anything else you assume about the sequence.
In this example, 2 examples, the domain and algebra are same, only the functions are different, right? So can we pinpoint the property of the function?
No, you will come back to these 2 examples to see why, at least in some cases you will see why it happened. Okay, in fact, you see, for example, the first example, I had more than just measurable functions, they even converged. And they were even a little bit monotonic. There are lots of things that were there in that function. Those are things that make it. But that doesn't mean they are needed to get that. See, the thing, there is no, very difficult to make a statement that this happens if and only if this happens. We can say if this happens, there are lots of sufficient conditions we can make. There is nothing like a necessary and sufficient condition which guarantee this. There is no theorem which gives you a necessary and sufficient theorem. I will come back to this example. Okay, so now we will look at, we will try to move from path to a better situation. What you did not assume anything about convergence. You simply said F1 is measurable. I don't care because lim always exists. Now suppose we will move towards a little bit favorable conditions where we can talk about limit. So suppose we had Fnx greater than or equal to 0, measurable. Same situation. But suppose we also assume, and now there is an additional term we are making, Fnx is monotone on decrease. Well, wherever there is a, for every x you can make a almost every x and throw away the set of measures 0. It's from whoever taking the long term. So sets of measures 0 are exempted from this. So then I can define the limit because fnx is increasing, therefore supremum is the limit. That may be a plus infinity, I don't care. That the extended real valued limit is, so we can define the supremum n because monotone not decrease. If fnx is bounded above, then fx is finite. If fnx at that point is not bounded above, then it is plus infinity. Okay, so fx could take plus infinity. So fx is less than infinity if fnx at an x, if fnx is a bounded sequence, bounded above sequence. Equal to infinity at x if fnx is unbounded. That's the possibility. You could have that it is infinity at all the points. Okay. The effect could be infinity at all the points. Okay. Then, even without this, Fatu is true. So I can straight away get Fatu's lemma. So by Fatu's lemma, limit omega fn d mu is greater than or equal to integral lim fn. But what is lim now? Limit itself. So it is integral omega limit which we call as. So Fatu straight away gives me that lim of f and d mu is greater than or equal to the integral of f d mu. This is one. Or we can write that as integral omega f d mu. So this is what it gives me. But on the other hand, fn's are increasing, fn's are an undecreasing sequence. So the limit is always the upper bound, least upper bound. So fnx is less than or equal to fx for every x because fn is non-decreasing. Fx is the supremum of all the fnx's and therefore fx must be greater than all the fnx's. If that is so, integral of fn will be less than or equal to, integral is a monotone thing. So integral omega fnx dv is less than or equal to fx. For every n. So if it is true for every n, the lim sup will be less than or equal to that. So that says the lim sup of integral omega fn du is less than or equal to integral omega. This is correct.
So, but can't we say that integral fn is an increasing sequence?
Say that again?
Integral of fn's are an increasing sequence of numbers.
Yes.
So you can take the limit itself.
Yeah, but I want to show that it is equal to integral. So eventually I want to show that I can interchange the limit. I know that integral fn converges to something. Why should it converge to integral f? All this says is integral fn's are bounded above. I want you have to assume that integral f is the least upper bound for that increasing sequence. That's not clear.
Correct. But Since we know that integral fn increases,
Yes.
the limit will be equal to the limit.
Yes. But what is the limit?
Let's keep it as some number.
Huh? Still that is less than or greater than or less than is only how you want. I want to show it is equal to. I want to show exactly that the limit integral fn is exactly equal to the integral of the limit fn.
Right, using just limiting in both 1 and 2.
Using the 1 and I have to use both 1 and 2. Yes.
Instead
Once
of-
I use 1 and 2, I am done.
Right, 1 and 2 you just use the limit is what
It says limit exists and equal to integral f. So let me write 1 and 2 what it says. Okay? What does 1 and 2 say? Start with 2. It says lim sup of integral f and d mu is less than or equal to integral omega f d mu. This is what 2 gives me. But now we take 1. Right? But then the limit this is less than or equal to lim sup because the lim sup of any sequence of number is always greater than or equal to the limit. So I have started with lim sup and ended up with lim sup. So I have to get equality all over the place. Therefore, lim integral fn equal to lim sup integral fn is equal to integral f. That says the limit exists and is indeed equal to integral f. Therefore, limit intending to infinity integral fn exists and equal to integral f. That integral f is the limit. So that's why I can interchange the limit and the integrals for such monotone and decreasing sequence of non-negative measures. So that is called in the monotone convergence. So omega b mu is fn mapping omega to r, let fn is greater than or equal to 0, non-decreasing, implies limit infinity omega fn is equal to integral omega. One comment. Both could be infinity. Both the sides could be infinity. That possibility exists. Because f could be infinity. So this could be infinity, that could also be. Both are finite, then you get the normal. So, one place where we are assured of the exchange of or the interchange of the limit and the integration is the monotone sequences. Now this is the one that is used to show that if you have a measurable function, I have constructed a sequence of simple functions which move up to that measurable function. So if f is non-negative, I can get a non-negative sequence of simple functions which go there. I can define the integral of these. And since it is monotone, the integral of this will converge to some number. It has to be integral f. In fact, that is how integral is defined. Okay? That is one way of approaching the definition of the integral, that it will have to it can be got as the limit of a sequence of simple functions increasing to f. Okay, now the second most popular theorem in this exchange of limit and integration is what is known as the Lebesgue dominated convergence. So far, we have been dealing only with non-negative functions, all these. Now we go to, suppose I have a measure space. Okay. And let me start with the following thing. Let me just keep doing measurable functions. I have a sequence of, when I am no longer assuming greater than or equal to 0. So I am just taking fn to be measurable functions. Now suppose see, now I am a little worried that I am even got out of the realm of non-negative functions. I don't have monotonicity, nothing. What am I going to do? I have lots of problems. So I will say, well, let me at least control the fn's. Suppose the fn's are all bounded. Let me put it that way, okay? Suppose there exists an m such that mod fnx is less than equal to m for every n and for every x. Suppose. So that at least let me handle first the controlled fellows, and then in uncontrolled fellows I will see whether I can approach them to uncontrolled. So suppose I have this control. What does this say? This says minus m less than or equal to fnx. Okay. So therefore, suppose I define hnx to be fnx plus m. What can I say about this function? Measurable function, constant functions are measurable, sum of two functions is measurable, and it is always non-negative. So it is greater than or equal to 0. Back to 40. I get? See, I know only Fatou's lemma, so I have to convert the problem to Fatou's lemma. So apply Fatou's lemma. To h and x. What do I get? Lim in integral omega h and d mu is greater than or equal to integral omega lim in h and d mu. Now let us what is lim in h and d mu? It is lim in fn plus m. So this will be lim in integral h and d mu plus m times integral measure of omega. That's a constant function, so I am integrating over omega. M times measure of omega is greater than or equal to integral omega lim in h and d mu. What is lim in h and d mu? Lim in h and is lim in, this is not correct, fn d mu plus now I can cancel m times measure of omega, provided that is finite. That is provided measure of omega is finite. So let's make an assumption. Suppose measure of omega is finite. Then I get lim in integral f and d mu greater than or equal to omega lim in not bad, some kind of Fatou's lemma I got, right? For these fellows also. Now I took these two and constructed a non-negative function. Take these two and construct a non-negative function. I get m minus fnx. So let me call this as 1. Then 2. Let umx be equal to what was that? M minus fnx. M minus fnx is greater than or equal to 0. I get lim of integral u and d. You get the integral lim u and d. Substitute for u and. What is lim of u and d mu? It is lim for minus f and d mu plus m times omega mu omega greater than equal to integral omega m times integral omega plus integral omega in of minus. Okay, you substitute it. Once again, I can cancel mu of omega because it is finite, has been assumed to be finite. Now, what is lim in for minus? Minus of lim sup. That's always something which you should remember. Okay, lim in for minus am is equal to minus lim sup of a. Okay, for any real number. So this becomes minus lim sup of f and d mu is greater than or equal to minus lim sup or lim sup of f and d mu is less than or equal to integral lim sup of this is true. Now what do 1 and 2 give? Lim sup is less than or equal to this, but this is less than or equal to the lim in. But lim in is less than or equal to lim sup. The same string of sequencing arguments. Again, therefore, lim in equal to lim sup is equal to. Do I get that? No. Because here I had lim in, there I get lim sup. So I don't get in the end equality. So what do? Suppose this and that are equal. Suppose Fn converges. Okay, so now I make the assumption. Suppose Fn tends to then I get this is the same as f d mu and this is the same as f d mu. Now compare the two. What do I get? Integral f d mu is great lim sup is Fn d mu is less than or equal to integral omega f d mu, which from there is less than or equal to integral Fn d mu. But this in turn is less than or equal to this because lim in is always greater than or equal to lim sup. So that says lim sup integral Fn equal to lim in integral Fn equal to integral Fn. Therefore, limit Fn exists, limit integral Fn infinity exists and equal to integral limit. Okay, so what are the things that we have had? If by chance they are all nicely uniformly bounded on a finite measure space and converge almost everywhere, then I can interchange the limit and the integration. That is called the Lebesgue dominated convergence theorem. I should somewhere, no, it's called Lebesgue bounded convergence theorem. Where shall I write? Because I want to point out something, okay? I will just summarize here. Lebesgue bounded convergence theorem. What does that say? Omega b mu finite measure space. Fn mapping omega to R measures. There exists M such that mod Fn x less than or equal to M for every M and for every x. Fn x converges to Fx almost everywhere. all that in black. Limit infinity integral of limit infinity, which is equal to that. Right? That is called Lebesgue bounded convergence. It is called bounded because there are bounded functions. Right? Now let's look at that again. Let me go through that proof again. I started with this. Then I had this, and I took that finite measure thing because I wanted n. Now this is too powerful a condition. I want the same bound to work at all points. We wanted a uniform bound for all of them. Suppose we did not have it. But at each point, point-wise it was bounded. Then this m would have been a function of x. And it's measurable. Why we want measurable, we will see. We would have got this. Then what would have happened to that theorem? This is what we would have got. Then what would have got here? Will I get m mu omega?
No, integral.
So I will get integral mx dv. Now I wanted to cancel that. All that I wanted to do was to cancel that. So all I needed was that the integral was finite. So if you assume that was finite, then the rest of it goes through. That is what is known as a dominated convergence. If you have a sequence of functions which are dominated by one single function now, which is having finite integral, then everything goes through. Okay? So what is the Lebesgue dominated convergence? It's exactly the same proof. Wherever there was this m, put mx, and where you wanted to have finite, then put that finite. Okay? So the Lebesgue dominated convergence. Now I don't need mu omega to be finite. All I need is integral g is finite. That's all. So therefore, omega b mu, let it says Fn mapping omega to r measurable. There exists a non-negative measurable function mx on omega such that mod Fn x is less than or equal to mx for every n and for every x in omega. So for every x in omega, this is true, and Fn x tends to Fn also. All other conditions. Then that says limit that is the dominated convergence. So in other words, what is the convergence, the integrals involving random variables is that either they must be uniformly bounded or they must be dominated by one random variable which has finite expectation. Integral gx must be finite. They are all dominated by a single random variable which has finite expectation. Then everything is. Right, okay, we are coming back to this more. So basically, therefore, you found to get this you use for 2, to get that you use for 2, to get this you use. That's why that's put as the base level to which you will always go. Convert everything. The idea is that non-negative is one thing which you should learn how to handle. The rest of the things can be brought back to non-negative things. So you have to handle non-negative measurable functions. And what to say, I don't even bother whether limit exists or not. I'll simply look at the general sequence and see what is the best I can get, and that is what is good. And the rest of them work. And this is the in a sense a great pull-up by Lebesgue from Riemann. Because in the Riemann thing, we were not even able to ask that question. If f and x were Riemann integrable, the limit function, even if it converged, the limit function may not be Riemann integrable. So therefore, the question of interchanging does not even make sense in general. Whereas in Lebesgue case, if you have sequence of functions measurable, the limit function is always measurable, lim inf is measurable, lim sub is measurable. So the two integrals are defined, and therefore it is natural to ask whether they are equal. So that is the thing. And it turns out that in many such cases this happens. I do not think there is any other theorem of if you have uniform convergence and all things are finite matter space, these are all very easy to exchange. Okay? But basically for a general situation, I think these are the three best theorems available. Monotone convergence theorem is for non-negative functions where you can actually interchange the limiting processes and the integral. Dominated and bounded convergence theorems are for general functions where you can actually interchange the limit and the integration. Fattou's lemma is only for non-negative functions where we don't even have limit, but we can still talk about some kind of a connection between the limit and the integral interchange. Okay, is it? Any questions?
Sir, we haven't yet proved that lim Fn is measurable. We have proved that.
Which is measurable?
Lim Fn.
We have proved it. When we talk about measurable functions, we have proved that lim is measurable. I should know that min is measurable. And from then I went, same argument worked for even min over k greater than or equal to m. And therefore the inf is measurable, sup is measurable, sup of inf is measurable, so everything is measurable.
Sir, and if you relax n instead of x, that is, if each function is bounded,
If each function
suppose
is
we have mn,
yes.
instead of being the function on x, suppose each function fn is bounded.
By what? By some constant.
m of n.
That doesn't lead you anywhere. It won't lead you anywhere. Again, some kind of lim I assume measure of omega to be finite, and then you may get some lim inf and lim sup, because integral mn I am not able to be cancelled now. Isn't it? So there will be an mn mu omega. So I will have to take a lim inf of that also. So there will be some problems there. So you will have to adjust that. So you are not going to get exact interchange of all, but you may make some statements about involving lim inf of mn. That integral. There is a more general theorem under some specific conditions, situations where what you are saying, not even but the fact that they are point-wise bounded will automatically force uniform boundedness. So again back to bounded convergence theorem for a certain class of functions in certain set of point-wise boundedness will automatically force uniform boundedness, and you straight away can apply bounded convergence. And then 1 less than or equal to m, and if you had a finite measure space, you can straight away apply bounded convergence. But basically, essentially these are the main theorems about interchange of integration and the limiting process. It will be either monotone, generally it will be either a conversion to a monotone problem or a dominant problem.
So, monotone and Fattou's lemma are equal identical.
They are not. Fattou's lemma makes sense even without monotonicity for any general sequence. Whereas monotone convergence theorem was for a specific thing, namely monotonically increasing sequence. In fact, incidentally, the interchange of when here the sequence was not increasing, this is false. This need not be true, by the way. So let's, for example, the Lebesgue monotone convergence theorem need not be true if Fn is non-increasing. Wanted monotone non-decreasing only. For example, you take Fnx, take omega to be R and the rest of the Lebesgue measurable set in the Lebesgue measure, Fnx to be the characteristic function of n to infinity. That is, Fnx is 1 here and 0 here. Okay, so what is integral Fnx? It is infinity. So what is lim in? Yes, lim in is this, right? Now, what is infimum of Fnx at kx for k greater than or equal to x? In fact, what is limit of Fnx? Is 0. Okay? So therefore, lim in of Fnx is 0. So the integral is 0. They get the same thing.
Integral of Fn is infinity.
Integral of Fn is infinity.
Whereas limit of the integral is 0.
Limit of the integral is infinity.
The integral of the limit is 0.
0. Doesn't that same thing?
They are not equal. You are giving a counter example.
Therefore, limit n tending to infinity, integral Fn is not equal to integral limit n. So whereas in the case of non-decreasing sequence, they are always, one was infinity and the other one is 0. So the non-decreasing itself, it is not so. Fatou's lemma is more general. It has no other assumption on the sequence. Only measurable sequence, that's all. Nothing else. Whereas here we have monotone sequence. So this is a monotone, this is not the right term. Lebesgue monotone is misleading, like it is true for monotone non-decreasing as well as non-increasing. It is monotone non-decreasing convergence theorem. Okay, now all these theorems are therefore offshoots of Fatou's lemma. Proof of Fatou's lemma. Okay, right. So therefore what remains is that if we have Fatou's lemma, we get a number of good convergence theorems. So what is this Fatou's lemma? So let's start. So let's see what we want to do. We are given non-negative measurable functions. So what I do is, let me fx to be the that's the notation. Okay. Instead of writing lim in every time, I will write fx. So now I want to compare the integral of f with the integrals of the fn's. That's what I want to compare. So first of all, what is integral? We have only one thing now, definition. It is the supremum of the integrals of all the simple functions which are below that. And we can take the simple functions to be non-negative because everything is non-negative here. So integral omega fd mu is equal to the supremum phi less than or equal to f, phi simple, measurable and greater than or equal to 0. This is what we want to. We want to show that this is greater than or equal to this. The left hand side is, the right hand side is this. This is exactly this. right hand side now. We want to show that the left hand side is greater than or equal to the right hand side. So, we want to show that this lim in is greater than or equal to that. Now, what is this lim in made up of? Okay. So, let's look at the following situation. Let us define G and X to be the infimum of this Fkx's for k greater than or equal to. Okay. Then, what happens to G and X?
G and X is less than Fkx for k.
What can I say about the sequence G and X? Many things I can say. What is one thing that you observe? What is it? Does it converge? It's just the mean,
Yes.
which is F. So G and X goes to F. How does it go? Does it wobble around or
No, from below it is.
goes up? So G and X's are increasing or non-decreasing functions to F. So G and X. For example, see this is, you take Fn x, Fn plus 1x, etc. You are taking the infimum from this stage onwards for Gn. For Gn plus 1, you are taking the infimum from this stage onwards. So you may get a bigger infimum there. So therefore, Gnx is less than or equal to Gn plus 1x. That one thing we observed. And another thing is Gnx is less than or equal to Fkx for every k greater than or equal to n, and Gnx increases to Fx. Roughly what does it say? Gn is going up to Fx and phi is to the left of Fx, then Gn will cross phi some stage, isn't it? For any phi, we are looking at phi less than or equal to F. Intuitively. Formally there are lots of technical difficulties that come into the picture. You first follow this intuitive line and then take care of the technical difficulties. Intuitively what this says is, these Gn's are all going up, F is here, phi is below, any phi is below or there, that's the problem, below or there, phi is less than or equal to F. But anyway, then the Gn fellows are going up and eventually they have to reach F, so they will have to cross phi somewhere. Okay, so therefore, if by chance I show that the Gn's are greater than or equal to phi at some stage, then they will be greater than or equal to phi at all stages. Because Gn's are all going up. At some stage if they are cross phi, all subsequent stages they will be beyond phi. If the Gn's are going to be beyond phi, the Fk's are going to be beyond phi after that stage. Right? After that stage, the Fk's are going to be beyond phi. If Fk's are going to be beyond phi, the integrals of Fk's are going to be beyond integral of phi. And therefore the lim of the integrals will be beyond phi, integral of phi. And therefore the supremum. And that result will be over there. That is the key ideas. Okay? So the intuitive argument first. Let me first write the intuitive argument.
You try to guess the proof intuitively. Try to guess the line of proof intuitively.
Yeah. So the intuitive argument. For any phi less than or equal to F, phi simple, okay? This is what we are looking at. For any phi less than or equal to F, since Gn increases, see all these are loose words, it is not decreasing and phi is to the left is not correct, phi may be sitting at F, all these problems, but intuitively, since Gn increases to F, Gn must be greater than phi. Here must be greater than or beyond some stage. Okay? If Gn's are there, that said, from that stage onwards, Fk's are all what What can I say about FKs? FKs are all greater than Gn. And therefore Fks will also be beyond 5. And Fk x is greater than or equal to Gn x for every k greater than or equal to n, because Gn is the infimum of all these fellows. And therefore this is greater than 5x beyond some stage. Now what does that say? This is the intuitive argument. We will write the whole thing. Therefore, integral of kx dx will be greater than integral phi x beyond some stage. If beyond some stage this is greater, the lim inf will be greater. Therefore, that will say lim inf of integral of k will be greater than this beyond some stage.
For every fee.
This is true for every phi, therefore the supremum also. That will say this is true for every phi. Therefore, the lim inf integral of k lim inf will be greater than or equal to the integral supremum over phi. Phi is equal to integral of f. And that is the argument. Okay? Now there are lots of problems about this technical thing that may come about in putting these argument pieces together. But all are circumventable. Okay? If you are careful enough, if there are technical difficulties, I will technically avoid them. That's all. Basic idea is this. Is that clear? The G's go to F, therefore they cross phi. If they cross phi once, they remain all the time after that. And by definition of the G, therefore F's will be beyond phi, you understand. F's are, the integrals will be beyond. The integrals are beyond, the lim inf will be beyond. And this will be true for every phi, and you are done. This is the line part. The rest of it is lot of epsilon delta garbage that goes into the. Is that clear? Is this argument clear? Now, one of the problems that may happen here is not a problem. See, I have no idea of how these fellows are. It may simply happen that this integral phi may be infinite for some phi. And the supremum itself is infinite. So, the integral f itself is infinite. So, there are certain crazy things like that, but that may happen. So, we have to handle all these cases very, very deftly. But it is not that difficult. Once you have this argument, are there any questions about this argument? This is the motivation of all the epsilon, delta, n epsilon, n delta proofs in the first lemma. The idea is you have this f. Now this f was approachable by its very definition by a sequence of functions increasing. And since phi lies to the left of f, this sequence will cross that. And that will give lots of information about the integrals, which you put them together and you get the. Okay, so that is the rough part. This is the intuitive proof, the technical proof. Now, as I said, this f is here, I said phi is to the left of f, and therefore it will cross. But I didn't say that phi is to the left of f. Phi can be sitting at f for some x. Phi x is only less than or equal to f. Then what do I mean by cross? I won't be able to cross. This whole argument falls through. This goes what? So you see, it was only intuitive. In the beginning itself, we may get into difficulties like that. What do you mean by cross? If phi fellow sits at f itself, then what happens? On many points of x, phi x could be equal to f of x. In which case, this sequence will not cross phi at all. Well, if it does not cross phi, here is a, suppose phi is sitting here for some reason. Well, take a slightly small portion of it. It will cross that. It will cross 1 minus alpha phi. For any alpha, then put alpha go to 0. That's the argument. Okay? So I can cross it. But then there is a difficulty there. The problem is if phi is 0, 1 minus alpha phi is 0, what do you mean by this crossing? F and phi may be sitting at 0 at that point. So, okay, therefore, let us look at the points where phi is greater than 0, because those are the things that are going to matter. In the integral where phi is 0, it doesn't matter at all. The integral is not going to matter. So you have to look at the points where phi is greater than 0. The person who proved this theorem must have wasted several sheets of paper. Let me know, okay, this is a problem. It is like you come up, somebody objects, you come up, somebody objects, or you yourself object your proof, go back and subtract that objection, some other objection comes into the picture, subtract that objection. Eventually, if you are lucky, you get a proof. But if your intuitive argument says it will work, there will be enough technical conditions which will guarantee that if your intuitive line of thinking is right. So therefore, first of all, let us look at this set, which is let 5. Okay, so we will work with that. Clearly, the integral of omega phi d mu is the same as integral b phi d, because the remaining places phi is 0. It's not going to contribute anything. Let's keep that in mind. Okay, so I'm going to go through this proof very slowly. You should understand, these are all, it's not the proof that is important. I mean, important is the way people thought, the way people think and how this is, most of them proof we write in a neat form, but that doesn't tell what went into the proof. So, we have this. We wanted to show somewhere along the line that the integral gk's are going to cross the integral phi's. That is our argument. So let us again define Gn, our definition, to be infimum k greater than or equal to n fkx, and therefore we have what? Gn increases to phi. That's non-decreasing sequence. Increases to? This is a non-decreasing sequence. My friend had a notation for this. It could be like this. Non-decreasing sequence for what else was there? Now, I look at this. Here is phi, 1 minus alpha. Because phi could be sitting at f, I go to the left of 1 minus alpha. So, I look at all those points, let 0 less than alpha less than 1. Look at the set of all those points x at which Gn crosses this 1 minus alpha. It has to cross. It has to cross at some stage because it's going to reach fx, and fx will be either here or beyond that. So certainly it is going to cross. So x is this, what shall we call this? Some am. Maybe I don't know, I call it as a equal to b. So I had in mind a as the original measure space, but suddenly I changed it to omega. Because I wanted to do it in a general space. Okay. So these are all the places where Gn crosses 1 minus alpha phi. So Gn crosses 1 minus alpha at the nth stage, it must cross for all. So we will write it as gkx for every k greater than or equal to n. Gkx greater than 1 minus alpha phi for every k greater than or equal to n. Now what do you see? Even in this, I am going to do quite a bit of intuitive thing before I put technical condition. An is clearly greater than like contained in an plus 1, because if it is greater than or equal to this after the n stage, it is also going to be greater than or equal to the list. Alright. Now, what can you say about that for integral gkx? It is greater than or equal to 1 minus alpha integral. Let me first write this. Is this correct? This is a smaller set. All are non-negative functions. I am taking only those places where it is greater than 1 minus alpha. But now, this is greater than 1 minus alpha by dv. But this is equal to, here is A, here is what is that, B, here is A. So I am integrating only over AN. So I can write it as, if I integrate over the whole of B, I will have to subtract the B minus AN portion. Okay? Now are we done?
So in the alien definition, should we say that x coming from B?
Yes, the other one is measure 0. I mean, we are going to be interested only in measure, so you are right, we are going to restrict only from other. Anyway, the other fellows won't even come here. Well, okay, even if they come with measure 0. If you want to put B, put B, it doesn't matter. It is okay. Because the rest of the, okay. So I got this. Let me. Right? But what is integral over B of this is the same as integral over omega. Because phi is 0 outside B. So finally I got integral over omega gk d mu is greater than 1 minus alpha integral phi d mu. That's what I wanted, somehow integral phi d mu, right? And minus B minus AN 1 minus alpha phi. Right? Now in this there are two things. One is minus 1, another one is plus alpha. So plus alpha part is positive. So if I remove that, it will become even smaller. So I can simply write it as minus this. Okay? So far any problems? Now, this is okay. That's what I want eventually. Integral gk is dominating the integral phi is what I wanted. Now this portion I can make like alpha go to 0, so there is no problem. What about this portion? If you look at integral phi d mu over B minus AN, phi, we are taking points in B as he pointed out now. There it is non-negative. So it will take only strictly positive values. How many of them? Only a finite number of them. And therefore, this will be controlled by either the minimum of phi into the measure of, I think minimum or max, I don't remember. Whatever, you can estimate that. One of them will dominate that. Okay. So therefore, I will get, there was an alpha there, minus, whatever it is. Suppose this goes to 0. Suppose that goes to 0. Measure of B minus AN also goes to 0. Then I am finished. Because now there is only an alpha which I can let go to 0, and this is true for every n, and I can do the limit. So basically therefore, does B minus n go to 0? right? I will rewrite the proofs again. There is usually, if you take a book, you will see a proof, case 1, case 2. Where do these two cases come from? Why do I need these two cases? Okay. So basically, therefore, does B minus AN go to 0? Now if you look at ANs are increasing. So B minus ANs are shrinking. B minus ANs are shrinking. Therefore, the limit of the measure will be the measure of the intersection. Provided original thing was fine. So provided B had finite measure. So once we have B as finite measure, everything goes through. Okay. Once we have B as finite measure, everything goes through. We can push through this argument. So you have to have two cases. B having finite measure, B not having finite measure. If B does not have a finite measure, that means this phi will have integral infinity. One of the parts must have infinite measure. So the integral will have infinity. So there arise two cases. One, where there is a phi which is less than or equal to f, for which integral phi is infinity. And the other case, where integral phi is less than infinity for all phi less than or equal to f. In both the cases, we will now handle the situation. That is the two cases that we understand. Is that clear? Okay, so next time I will write the proof again in detail. This proof, Egorow's theorem proof, these are all a sort of real convergence ideas are all built into that. See, the thing is, it is not only convergence of the function, it is convergence of the measures, convergence of the sets, everything is built into that. So if you understand these 2-3 theorems proofs, you get really the essence of convergence. So I will go through this full proof, because right now if I start I will not finish. Anyway I will have to start again. So again for this lemma. Now next time if I start two cases, you should not ask why should I thought this. The two cases are because of that. Fatu did not write straight away, consider case 1, consider case 2. Where? He will fully to do that. He went through. See, first thing is, you bulldoze your way through. Go on doing things. Okay, here maybe I need an assumption. Put there a circle, going. I will put the right assumption there. Go. Finally, do I get anything at all? If I got something interesting, then go back and settle the technical. If I got nothing, why waste your time trying to fix the technical condition? They are not useful anyway. So you have to bulldoze your way and see where exactly you need what condition. So you will see. Therefore, if in every one of these cases, where exactly I needed that condition, why I split it into two parts, etc., etc. The argument is simply started with this. If Gn is going to reach f and phi is below f, Gn will have to cross f sometime. If that happens, I am done. Now, once this got into his mind, he bulldozed this way and got the good answer. I think I will prove the theorem in the next class. That's one of the best theorems. Unfortunately, it's called lemma. I don't know whether it's something demeaning to call something a lemma or what, I don't know. Theorems are supposed to be of higher level. But nowadays, any result everybody writes as a theorem. You take any paper, if I have proved a result, it's a theorem. Okay. So the meaning between theorem and lemma has been lost. Okay, I will continue with next time. Yeah, last time I made a comment which I said that in the next 4 or 5 classes, analysis will go over, it will not go. Probably convergence will go over. Okay, a lot of things, particularly differentiation, the connection between integral and we had that has to be established. That is that is called the fundamental theorem of integral calculus. We have not yet done. I have not yet done analysis. See, first we had differentiation for some reason came first because of Newton. So physics was first. Then came anti-differentiation, which we teach in college as integral calculus. Okay. Then came the so-called definite integral. which is what integration is. And somehow or the other we were told in school that if you want, once you know anti-differentiation, to calculate indefinite integral you have to simply substitute the upper limit and the lower limit and take the difference. That was the magic. Nobody said why it happened. Okay. And that is the connection between all these three. Okay. So that is called, that I have to start. So first I will have to do all this basic. I already done quite a bit of ingredients about differentiation and the thing about linear derivatives and all I have done. But there is a real connection between this integration and differentiation and this antiderivative. And that is the fundamental theorem. So in other words, that the antiderivative is the integral. Indefinite integral is the fundamental theorem of integral calculus, and that requires quite a bit of work again. And then the LP space. So it is not that 4, 5. I think he was worried that 4, 5 to be over. Analysis is never over. It's not all this. As I said, I remember 30 years back there was a conference in University of Delhi on functional analysis. I repeat this that when the last day afternoon, the chairman decided the university, vice chancellor was a mathematician at that time, Delhi University. So he decided that we will have one session in the afternoon where we will discuss what should be the standard good curriculum for senior graduate students in functional analysis, for functional analysis. So he requested Professor K.R. Parsarthi to chair the discussion and asked him to make the initial remarks to start the discussion. And Professor K.R. Parsarthi made the comment that functional analysis begins where linear operator ended and non-linear operators begin. Our functional analysis today is where linear functional analysis ends and non-linear functional analysis begins. All the people who have come to present papers have worked on linear operator theory. Not a single fellow was there. There was chaos after that. This is more or less condemning all these fellows that you are out of tune of what's happening with functional analysis now. So in that sense, it's never ending. See, this one thing ends means something else begins. That's all. It is not the end of it. But there is, even in the first stage end, there are a few more things that have to be pitched in here. And that, once I do also see, that will be a good course, graduate level math course comparable to anywhere else in analysis. Okay. Continue on.